Welcome to my Math Explainer video. Today we will be learning about eigenvectors, how they work, and how they can be applied to real-world problems. So what is a matrix really? A matrix is not a grid of numbers. It is a motion that moves every vector in the plane. We will follow this one, A, the whole way. Here's the plane, every arrow on its own line. Apply the matrix. Almost every arrow swings off its line to point a new way, but two of them refuse to turn. They only stretch. Those two stubborn survivors are the eigenvectors, and the number each one stretched by, 4 and 2, is its eigenvalue. So an eigenvector is a direction the matrix only scales, and its eigenvalue is how much. That is all this equation says. Matrix times the vector equals that number times the vector. These are the directions the matrix treats as its own. Eigen is German for its own. Find a matrix's eigenvectors, and the hard things, powers, motion over time, the spread in data, all become easy. That is the promise of this lesson. Sit with how strange that equation really is. Two names to pin down. The surviving vector is the eigenvector. The number it scales by is its eigenvalue, lambda. The equation just pairs them. On the left, a full matrix multiplication. On the right, multiplying by a single number. For an eigenvector, they give the exact same answer. We rule out the zero vector since it satisfies the equation for every lambda and tells you nothing. An eigenvalue, above 1 stretches, between 0 and 1 shrinks, negative flips the vector around. And an eigenvalue of exactly 0 means the matrix crushes that whole direction down to a point. That is the surprise. A matrix is full of numbers, yet along an eigenvector, its entire effect is just 1. That last case, eigenvalue 0, is worth watching for real. First, the two arrows you will keep seeing. I hat is 1 step along x. J hat is 1 step along y, and every vector is built from these two. So where they land is the entire matrix, it's 2 columns. This one has eigenvalues 1 and 0. It leaves I hat alone, but sends J hat to 0. Watch the yellow arrow drop straight down onto the x-axis like a shadow cast from above. Its height is gone, and the unit square flattens to a segment with 0 area. Throwing a whole dimension away is exactly what determinant 0 or singular means. You cannot recover the height you lost, so this matrix has no inverse. A quick check before we go on. Two numbers you can read off any matrix in seconds, and both are secretly its eigenvalues. The determinant is how much the matrix scales area. Our unit square grows into a parallelogram. Cut that parallelogram into equal cells and you can count them. 8 of them fit, each the size of the square we started with, so the area grew 8-fold. That is the determinant. By the rule, a times d minus b times c, 9 minus 1 is 8. And 8 is exactly 4 times 2, our two eigenvalues multiplied. Eigenvalues always multiply to the determinant. The trace is even easier. By a plus d, just add the diagonal. 3 plus 3 is 6, and 4 plus 2 is 6 as well. Eigenvalues always sum to the trace. So before trusting any eigenvalues you compute, add them and multiply them. Miss the trace or the determinant, and you know you slipped. The trace has a picture too, if you watch area in motion. Ease the transform on by a fraction t, from nothing at 0 to the full matrix at 1, and watch the area of a little patch. It starts at 1 and climbs. Its launch speed, the slope right at the start, is exactly the trace, which is 6. The straight gold line rises at a steady rate, 6t, and that rate is the trace, how fast the area starts growing. The blue curve then bends up above it, and that extra bending is the determinant taking over. So the trace sets the early speed, the determinant the final size. And the sign of the trace is what decides the direction. A positive trace inflates the area as it starts to move. A negative trace shrinks it from the very first moment. But how would you find these directions from scratch? Start from the definition. With v an unknown direction and lambda an unknown number. Move everything to one side. Lambda times v is lambda times the identity times v. Now factor out v, we need a non-zero v that this new matrix sends to 0. This is the squashing square from before. We need a minus lambda, I to go flat, crushing a non-zero v onto the origin, and a matrix only does that when it collapses area to 0. That is determinant 0. So the eigenvalues are the amounts you subtract from the diagonal to make the matrix go flat. This is the characteristic equation. Put our matrix in and take the determinant. Multiply it out and it flattens into a humble quadratic, the characteristic polynomial. Factor it. The roots are 4 and 2, exactly the stretch factors we saw by eye. We started from pure geometry, arrows refusing to turn, and landed on the roots of a quadratic. The picture and the formula just shook hands. Each eigenvalue hands you its direction. Start with lambda equals 4. Subtract it down the diagonal to get this matrix, and find the v it crushes to 0. Write a minus 4. I times v equals 0. Multiplying it out gives 2 equations, one from each row. But both rows say the exact same thing, y equals x. They have to, because we picked lambda to make this matrix singular, so its rows are proportional. One real equation, not 2, and one equation is a whole line of solutions. Every vector with y equals x works, so we picked the simplest 1, 1. Now lambda equals 2, subtract 2 down the diagonal instead. Same story. Both rows collapse to x plus y equals 0, so y equals minus x, the direction 1, minus 1. The 2 arrows from the start now derived. In real life, you would not grind this by hand. You would use software or write code and read the answer off, scaled to length 1. And an eigenvector is only a direction. The negative of what you expected is the same eigenvector pointing the same way, and there's a picture hiding behind that algebra. Here is that singular matrix, a minus 4i. Watch what it does to the whole plane. It collapses everything onto a single line. I hat and j hat both fall onto it, and the gold arrow, 1, 1, is crushed all the way down to the origin. That crushed direction is the eigenvector. A minus 4i sends 1, 1 to 0, which is exactly the equation we just solved. So finding an eigenvector is nothing more than asking which direction the collapse sends to the origin. Notice a gift hiding in this example. Look again at our 2 eigenvectors along 1, 1 and 1, minus 1. They sit at a perfect right angle, 90 degrees apart. Apply the matrix. They stretch 1 by 4 and 1 by 2, but they never twist off each other. The right angle survives. That is no accident. Flip the matrix across its diagonal. The green one and the blue one trade places, but both are 1, so the matrix is completely unchanged. A equals its transpose. It is symmetric. And being symmetric is a kind of promise. A symmetric matrix can only ever stretch space along perpendicular axes like these. Soon we will meet matrices that misbehave, and symmetric ones simply never will. It is why symmetric matrices, covariance, stiffness, graph Laplacians are the heroes of every application coming up. Does any of this survive in higher dimensions? Take this symmetric 3 by 3. Notice every row sums to 4. Multiply it by the all ones vector. Each output is just that row added up, so you get 4, 4, 4, which is exactly 4 times 1, 1, 1. And that is the whole point. The matrix did not turn that arrow at all. It only stretched it 4 times longer in the same direction. That is precisely what makes 1, 1, 1 an eigenvector, and 4 is its eigenvalue. Now lambda equals 1. Subtract 1 from each diagonal 2, so every 2 on the diagonal becomes a 1, and the whole matrix turns to all 1s. Now all 3 rows are identical. The single equation, x plus y plus z equals 0. Why only one equation? All 3 rows are exact copies of x plus y plus z equals 0, so 2 of them tell you nothing new. 3 identical rules are really just one rule. And one rule on 3 numbers leaves 2 of them free, with the third forced, and 2 free directions is exactly a plane. It is the same counting as in 2 dimensions, where the single rule, x plus y equals 0, left one number free and traced a line. Add one more dimension of freedom, and that line fills out into a whole plane. So the repeated eigenvalue did not give one direction, it gave a stubborn plane, a 2-dimensional eigenspace. A fearsome-looking 3x3 is really doing one simple thing, a single stretch along the diagonal axis. The method scales to any size. Only the polynomial gets harder to solve, never the underlying idea. Sit with that repeated eigenvalue because it does something new. Here's the plane the matrix leaves alone. Every vector with x plus y plus z equal to 0. Remember, the equation left 2 numbers free, so pick 2 directions inside the plane, call them v1 and v2. Now here's the point. Every other arrow in the plane is just a blend of those 2 free directions, and their blends sweep out the entire plane, and every single one is an eigenvector with eigenvalue 1. Only the one direction poking out of the plane, 1 and 1 and 1, gets stretched by 4. In 2 dimensions, an eigenvalue could only ever claim a single line, one free direction. Here the repeated eigenvalue claims an entire flat sheet, 2 free directions. That is what a 2-dimensional eigenspace means. The eigenvalue does not own one arrow, it owns a whole plane of them. But some matrices are stranger, and the strange ones teach the most. Here's a matrix that rotates the plane a quarter turn. Watch every arrow swing a quarter turn to a brand new direction. Not one lands back on the line it started on, so no direction survives. And there is no real eigenvector. Here is the deep reason. A real eigenvalue can only stretch a direction along its own line. It can never turn one. But this matrix turns everything, so no real number can possibly describe it. We need numbers that turn, and that is exactly what complex numbers are. Multiplying by I is a quarter turn, order. So solve for its eigenvalues. The characteristic equation is lambda squared plus 1 equals 0, which has no real answer. You are forced into the imaginary. Lambda equals plus and minus I from a matrix of ordinary real numbers. That is not a mistake. It is the algebra waving a flag that says this transformation rotates. Complex eigenvalues are the natural language of anything that spins or oscillates, like circuits and orbits. The first time you see them, it feels like something broke. It did not. The math is being honest. And that imaginary number has a clean picture. Plot the eigenvalue on the complex plane. Real numbers run across, imaginary numbers run up. Our eigenvalue. I lands right here, 90 degrees around the circle, the very same 90 degrees as the rotation. The angle of the eigenvalue is the angle it turns. Its partner minus I sits opposite, and both sit exactly on the circle. Distance 1 from the center, so there is no stretching, just a pure quarter turn. So a complex eigenvalue is just a rotation, written as a point. Its angle is how far it turns, and its distance from the center is how much it scales. Sit on the circle and it is pure rotation. Outside, it also grows. Inside, it shrinks. That single picture drives the stability of every spinning, oscillating system. Now a matrix that shares an eigenvalue but loses an eigenvector, a shear slides every point sideways by an amount equal to its height. The whole plane slides. Only the horizontal axis at height 0 stays put. Every other arrow tilts off its line. Solve for the eigenvalues. The characteristic equation is 1 minus lambda squared equals 0. So lambda is 1, but it is a double root. It appears twice. Now the eigenvectors, a minus ascends every height down to the x-axis. So only vectors with height 0 survive. That is just one direction, 1, 0. Here's the catch. The eigenvalue arrived twice, but it handed back only one eigenvector. The repeat in the number is not matched by a repeat in directions. A matrix short on eigenvectors like this is called defective, and that shortfall is exactly what stops it from being diagonalized. Contrast the symmetric 3 by 3, whose doubled eigenvalue filled an entire plane. A repeated eigenvalue is a fork, sometimes a whole plane, sometimes it comes up short. So we have now seen a repeated eigenvalue land in two different ways. It filled a whole plane for the 3D matrix, but only a single line for this shear. Why the difference? It comes down to two different counts, and they have names: algebraic multiplicity and geometric multiplicity. They usually agree, which is why they feel like one idea, but they really measure different things. One we read off the equation, the other off the eigenvectors. Algebraic multiplicity lives in the equation. For both matrices, the factor for lambda 1 is 1 minus lambda squared. That little exponent 2, sitting up there, is the algebraic multiplicity. In plain words, the equation promises the eigenvalue 1 twice for each of them. Geometric multiplicity lives in space instead. It is simply how many independent eigenvector directions you actually get. The symmetric matrix handed back a whole plane, 2 full directions, so its geometric multiplicity is 2, but the shear handed back only a single line, so its geometric multiplicity is just 1. And now you can see why we ever needed two separate words. The symmetric matrix was promised 2 and delivered 2, a perfect match, and a match is what lets a matrix diagonalize. The shear was promised 2, but delivered only 1, and that gap between what was promised and what showed up is the entire meaning of defective. So the rule: geometric can never beat algebraic and never drops below 1. Match it everywhere and the matrix diagonalizes. Any gap at all, and it is defective. Now the promise from earlier finally pays off. The rotation hid imaginary eigenvalues. The shear came up an eigenvector short. A symmetric matrix can do neither. Always real eigenvalues, always a full set, and always perpendicular. That guarantee is the spectral theorem. Nobody finds these by hand for big matrices. So how do you actually find these in practice? By hand, the characteristic polynomial is the right tool, and it works beautifully for a 2 by 2 or a tidy 3 by 3. But it falls apart at scale. Abel and Ruffini proved there is no general formula for the roots once you pass degree 5, and even chasing the roots numerically is wildly unstable. So real software never builds the polynomial at all. Instead, it works on the matrix directly by iterating on it over and over. Power iteration finds the single top eigenvector. The QR algorithm finds all of them at once, and Lanczos handles enormous sparse matrices with millions of dimensions. And power iteration is the humblest of all. You just multiply the matrix by a vector, normalize, and repeat. That one tiny trick is what will soon let us rank the entire web. One last practical tip. When your matrix is symmetric, reach for the routine, called A rather than AG. It is faster and it guarantees real, clean, perpendicular eigenvectors. Once you have them, the real payoff begins. And here's the deepest thing those eigenvectors unlock. A diagonal matrix with numbers only down its diagonal is the simplest kind there is. It just scales each axis on its own with no mixing, so even its powers and its exponential are trivial to work out. So the prize is to make our tangled matrix look like one of those pure scaling. That is diagonalization, and the eigenvectors you just found are exactly the axes that pull it off. So watch two different kinds of axes at the same time. Watch the standard axes. The matrix tilts I hat, which pointed straight along X, partway, up into Y, and tilts J hat the same way, across into X. Each one bleeds into the other, so neither lands back on its own line. That bleeding is exactly the off-diagonal ones in the matrix. And here's that bleeding as plain numbers. The new X is 3X plus 1Y. So to find it, you must borrow little of the old Y. That borrowed 1 times Y is the off-diagonal one, and it is the mixing. A diagonal matrix has a 0 there, so nothing is borrowed, and each coordinate stays in its own lane. But the two eigenvector axes in gold only stretch by 4 and by 2, and never mix at all. And that is the whole secret. A direction the matrix only scales is exactly what an eigenvector is, so the eigenvectors are the only directions that never mix, which makes them the only axes that can ever turn this matrix diagonal. So stop using the standard axes. Describe this same matrix along its own eigenvectors instead, and every bit of mixing simply vanishes. It becomes pure scaling, 4 one way, and 2 the other. And that is the whole idea. Diagonalization is the very same transformation. Seen from the axes where it is simplest, a clean diagonal D. The off-diagonal mess was never real, only the wrong point of view. And that simple picture hides a surprising amount of power. We know A is secretly diagonal in the eigenvector axes, but to put that to work, or to raise A to a power, or take its exponential, we need a formula linking A back to that diagonal D. Here's how to build one. Start from what we already know. A stretch is its first eigenvector by 4 and its second by 2. Only those two facts. Take the two eigenvectors and stand them up as the columns of one matrix. Call it P. Its columns are literally the eigenvectors. Now multiply A by that whole matrix. A just hits each column, so the columns become 4 times V1 and 2 times V2. But that is only P again, with its columns scaled by 4 and 2. Slide those two numbers onto the diagonal of a matrix D, and we have AP equals PD. Finally, peel the P off the right by multiplying both sides by its inverse, and there is the formula built by hand. And that inverse only exists when P has a full set of independent eigenvector columns, exactly the condition we kept needing. And read right to left, it is a recipe. P inverse rewrites any vector in eigenvector coordinates. D scales each one by its eigenvalue. P brings it back. In those coordinates, the tangled matrix is nothing but stretching. And now watch why powers get cheap. Multiply A by itself, and in the middle, every P inverse meets a P and cancels to the identity. All that survives is D raised to the n. So A to the 10th, which is 10 full matrix multiplications the long way, becomes just 2 numbers raised to the 10th, 4 and 2. That is the entire saving. And that very same cancellation runs through the matrix exponential e to the a, the tool that solves systems evolving over time. Diagonalize once, and the hard things turn easy. And hold on to these two, powers and the exponential, because they are about to run the rest of this story. Ranking the entire web is just powers of a matrix. Whether a system holds together or blows apart is its exponential. This one formula is the engine under both. In the right coordinates, a diagonalizable matrix is just a list of independent stretches. Its tangled look was only the wrong basis, and its eigenvectors are the basis where that illusion drops away. But every line of this needed a full set of eigenvectors. Remember the shear? It came up one short. Defective. So it can never be written this way. Shut out of cheap powers, exponentials, all of it. That is the real reason multiplicity mattered. A full set, and this whole toolkit opens. A gap, and the matrix is locked out. That shortfall is exactly what defective costs you. So there it is. A equals PDP inverse, built entirely from the eigenvectors. Now let us name what each of those three letters actually is. P is the eigenvector matrix. Each of its columns is one eigenvector of A, the new axis you switch into. D is the diagonal of eigenvalues. Each one is the scale factor for its own eigenvector with zeros everywhere else. And P inverse is simply the inverse of P. It rewrites a vector in those eigenvector coordinates, so D can scale it. Then P brings it home. Notice it is P inverse that goes in and P that comes back. A spot even some explanations get backwards. Here's where it ranks the entire internet. Now the payoff. Here's a tiny web. Each circle is a page, and each arrow is a link from one page to another. Turn that web into a matrix, M. Each column says where one page sends its score, split evenly among its links. Read down C's column, and you see C sends half to A and half to D. Exactly, it's two arrows. And the scores themselves are a vector, V, one number per page. Start them all equal, a quarter each. Now pass every score along its links at once. That single handoff is exactly M times V. C is the page the most arrows point at. So after one round, it has already pulled ahead. Do that multiply again and again, and the numbers stop moving. They freeze at this vector 0.2, 0.2, 0.4, 0.2, with C on top. And look, multiplying it by M now hands back the very same vector. And why is the eigenvalue exactly 1? Look down the columns of M. Every single one adds up to 1, which means each page passes on its whole score. Nothing created, nothing lost. So the total importance is fixed forever, and a steady state that can neither grow nor shrink is precisely what an eigenvalue of 1 is. So these four frozen numbers are the page ranks themselves, the eigenvector with eigenvalue 1. C's entry is the largest, so C is the top result, and you rank the whole web just by sorting this one vector. So converging is not abstract. It means the rankings have settled into the one self-consistent set of scores, where each page's score equals the importance flowing into it. C wins not just for having the most links, but because the pages pointing at it are themselves important, and they funnel that weight straight in. Important pages make the pages. They point to important. And start the bars anywhere you like. They always settle on these same scores. The ranking belongs to the link structure itself, not to where you began. Finding it is nothing but this. Multiply, pass the scores along, repeat. That is power iteration, and it is how Google ranks a web of 1 billion pages without ever solving a polynomial. But on the real web, this simple version has a catch. Here's the same idea, but watch one bad spot break it. Pages T1 and T2 link only to each other, a closed trap, and page A keeps feeding into it. Start every page equal again and pass the scores along round after round. But the surfer who wanders into the trap can never get out, so every bit of importance drains into T1 and T2. Look at the ranking now. Every other page has collapsed to 0. It is useless. So Google adds a tiny escape. On each step, with about 15% chance, the surfer ignores the links entirely and jumps to a random page. That leaks importance back out of the trap. And now the scores recover. The trap still scores high, fairly, but every page gets a real share again. That 15% jump is the damping factor. It also quietly fixes dead ends, pages with no links at all where the surfer would otherwise vanish. The teleport always gives it somewhere to go. Now write that one rule down as a single matrix. Start from the plane, link matrix, where each entry of M is just a click probability. From page J, every one of its outgoing links is equally likely. Google's fix is a two-choice rule with probability D about 0.85 follow a link, otherwise jump to a random page. Teleporting to a uniformly random page is the matrix where every entry is 1 over n, the all ones matrix scaled. Blend the two options by their probabilities. That weighted average of the link matrix and the uniform jump is the formula. So the formula is not algebra. It literally says, with probability D use the links, otherwise teleport to a random page. The teleport makes every entry positive, which guarantees one unique steady state and makes the iteration converge fast. 0.85 is the deliberate sweet spot. Those same eigenvectors also shrink data. But first, why is there ever so much of it? Real data is enormous. This little photo is a 10 by 10 grid, 100 pixels. So it is 100 numbers, a single point sitting in 100-dimensional space. A real photo is 1,000,000, but a face does not vary in 100 independent ways. Change just a few things. Who it is, the angle, the lighting, the expression, and you have covered almost every face there is. So 100 measured numbers hide only a handful of real ones. That gap between what you measured and what actually varies is pure redundancy, and finding it is the whole job. To find those few real directions, we just need two simple ideas first: variance and covariance. We will watch them on a cloud with just two dimensions, x and y, so we can see it, but everything works the same up in 100. Variance is just spread. Flatten every point onto the horizontal axis in gold, and it covers this wide range that is the variance in x. Flatten onto the vertical axis instead in orange, and the range is far smaller, the variance in y, but x and y are linked. Whenever a point sits to the right, it also tends to sit high. So the points pile into these two green quadrants. Measure that leaning, and you get the covariance, positive here, and it is exactly what tilts the cloud. Now build the matrix from those three numbers. Every entry is just an average over all the points. You take each point's gap from the center and multiply. The two spreads land on the diagonal, and the covariance fills both corners. That grid is the covariance matrix. Drop in the numbers from this very cloud. The spreads, 4.9 and 1.5, on the diagonal, and the covariance, 2.1, in both corners. There it is. Derived, not handed to you. Notice it is symmetric, the same covariance in both corners, and a symmetric matrix, by the spectral theorem, always hands back perpendicular eigenvectors and real eigenvalues. So its eigenvectors are perpendicular axes through the cloud, and each eigenvalue is the variance along its own axis. Those axes are the principal components we are about to find. And here's the punchline. Diagonalizing this matrix, rotating onto its eigenvectors, drives the corner covariance to 0. In those axes, the data is uncorrelated, just two clean, independent spreads. Now those same eigenvectors will shrink your data. Here's the goal. Right now each point costs two numbers, its x and its y. We want to describe every point with fewer numbers than that, ideally just one, and barely lose anything. That is all PCA is. Step 1, find the direction the data varies the most. That is the first principal component, and it is simply the top eigenvector of the covariance matrix we just built. almost all of the spread lies along it. The second direction is perpendicular, and the data hardly varies along it at all. Every point is nearly the same there, so that direction carries almost no information. It is the one we can afford to throw away. Now take just one point. To say exactly where it sits, you need two numbers. How far across, that is x, and how far up, that is y. Two numbers for one point. Now slide that point straight onto the first line. Where it lands is a single number, simply how far along the line it is. The point did not vanish and nothing merged. Its address just shrank from two numbers to one. Every other point works the very same way. Drop them all onto that line. Keep only those landing spots and the flat cloud becomes a single line of points. Each one went from two numbers down to one, and since the direction we dropped barely varied, the points hardly moved. The data is compressed, and almost nothing is lost. And the eigenvalues tell you exactly how much you kept. Each one is the variance, the amount of information, along its eigenvector. And here, the long axis held almost all of it. That is why a single number was enough. Now be honest about the cost. This is lossy. The sideways part you dropped is gone for good, so you can never rebuild the exact original point, only its shadow on the line. But here's the quiet part. You almost never want the original back. Because the direction you threw away was the smallest and shakiest one, it is very often just noise. So the rebuilt data can come out cleaner than what you started with. You did not only shrink the data, you quietly stripped some of its noise. So this is really not about saving space. It is about keeping only the directions that carry the signal. Fewer, cleaner features train faster and overfit less, so the answers come out better, not just smaller. The one catch is that it only pays off when the direction you dropped really was junk. Drop one that mattered and you have simply lost information. And it all scales. A point with 100 features usually hugs a flat sheet only a few directions wide, so the top 3 or 4 eigenvectors capture nearly everything. 100 numbers become 3. That is image compression, eigenfaces, and the first step of countless machine learning pipelines. And they decide whether a system holds together. Many systems evolve. By x dot equals ax. Drop a point anywhere on this plane, and it drifts along the flow of the matrix. Both eigenvalues are negative, so release the points, and every single path slides inward and settles at the center. That is a stable system. Watch the two eigenvector directions in green. Along them, the motion is pure shrinking, and every other path is just a blend of those two decaying modes. And look at the corner. Both eigenvalues sit in the left half of the plane, the stable region, because a negative real part means decay. That is the entire test. If every eigenvalue has a negative real part, the system always settles no matter where it starts. Flip one eigenvalue positive and watch. Now a matrix with one positive eigenvalue. Release the very same points and watch what changes. Along one eigenvector, the flow still decays inward, in green. But along the other it grows, in red. And that one growing direction flings everything out to infinity. It does not matter that one mode still decays. The single growing mode always wins in the end, and the state runs away. In the corner, one eigenvalue has crossed into the right half of the plane. That alone is enough. Stability is unforgiving. Every last eigenvalue must stay in the left half plane, or the whole system is unstable. And when the eigenvalues turn complex, then the straight paths bend into curves, and the whole flow begins to turn. The point spirals. The imaginary part sets how fast it circles, and the real part, still negative here, keeps pulling it steadily inward. So a complex eigenvalue with a negative real part is a damped oscillation. It rings and it settles like a plucked string fading to silence. In the corner, the pair sits off the real axis, but still on the left. Push them across to the right, and the spiral would wind outward instead. Which half of the plane the eigenvalues live in is the one rule that decides whether a drone hovers, a power grid recovers, or a reactor runs away. From bridges to networks, it is the same idea. A guitar string or a bridge vibrates in its eigenvectors, the normal modes, each at one pure frequency. Drive a structure near one of those frequencies and the matching mode resonates and grows. That is why soldiers break step on a bridge, so their rhythm does not match its natural frequency. Write a network as its Laplacian, a symmetric matrix, and the eigenvectors split it cleanly into communities. The number of zero eigenvalues even tells you how many disconnected pieces the graph has. Spectral clustering, image segmentation, graph layout, all of it rides those eigenvectors. PCA uses a covariance matrix, a vibration, a stiffness matrix, clustering a Laplacian. 3 fields, 1 idea, always symmetric. A few traps before we close. For our matrix, the diagonal reads 3, but the eigenvalues are 4 and 2. They are not the diagonal. Any non-zero multiple of an eigenvector is the same eigenvector. Sign and length are free. A repeated eigenvalue does not promise enough eigenvectors, so always check before diagonalizing. And complex eigenvalues are never an error. They are the algebra telling you something rotated. 3 cross-checks catch almost every slip. Sum to the trace, multiply to the determinant, and each lambda makes A minus lambda I singular. So, the whole subject in a few lines. A transformation knocks almost every vector off the line it started on. The few that survive, that only stretch, are the eigenvectors, and each scales by its eigenvalue, lambda. You find them by asking which lambda makes A minus lambda I collapse space. Once you have them, the matrix diagonalizes into pure stretching in its own natural coordinates. Which is why ranking the internet, a bridge shaking apart, and a photo staying small are all one equation in disguise. That is eigenvectors, the directions a matrix leaves alone, and the numbers that say by how much.